This is Mrs. O'Neill for AP Chemistry, Chapter 5, Section 1. This chapter is on thermochemistry. So thermo, hopefully that reminds you of heat. So we're going to be talking about heat and what that really means. Again, don't see too many chemistry jokes or cartoons, so when I do, I try to put them in here. If you notice, this one's from 1993. So again, go through those terms on page 194 and make sure you are familiar with them. Chances are you've heard the word energy today, perhaps in one of your courses, in the news, in conversation, or possibly in all of these instances. Our modern society depends on energy for its existence. The issues surrounding energy, its sources, production, distribution, and consumption pervade a lot of our conversation, from science to politics to economics to environmental issues. So you should have watched 2 introductory lessons before you even started the packet. The first one was on temperature. So these are my notes that I took. He talked about temperature being the average kinetic energy of molecules. So remember, molecules are constantly in motion, especially gas molecules, but all molecules, all atoms are in constant motion. So temperature is just going to be the average. How fast are they moving on an average basis? So what happens, or how does that thermometer go up in temperature? Well, your molecules are going to be speeding up. They push more on each other. They hit each other. They hit the sides of the container more. And a lot of times things are just expanding. So, of course, when we heat things up, just like we did in our magnesium oxide lab, you heated up that crucible, but waited a few minutes until you massed it out because you did not want to mass it out very, very hot. You would be massing out the expansion as well as the crucible and the magnesium oxide itself. Again, he gave you some flow charts, and he talked about that absolute zero, which is 0 degrees Kelvin, something we haven't attained yet, but we're in the process of doing, and hopefully we'll be there soon. I know that we're in a few degrees of zero. So he also talks about the Maxwell-Boltzmann distribution, and we're going to talk more about this also in later chapters, but it's just, how do these molecules distribute? How are they going to distribute in different temperatures as well? So he put that food coloring in 15 degrees Celsius water and 65 degrees Celsius water, and as you notice, the more heat, or I should say the warmer the water, the more those molecules are going to be moving around. So everything is in molecular motion, like we said before. So obviously the faster the water molecules move, the more they bump into the food coloring, and the path is random. So we want to make sure that we understand that, you know, you got your water molecules all over the place, and they are also moving, but they're going to be moving faster at a higher temperature, causing the food coloring particles to be moving also faster, or distributing faster throughout. So these moving molecules, again, they're at different speeds, and so that's why we take an average. Just like anything else, you have people who walk the halls. Some of them walk them pretty quick. Some of them walk rather slow. So if we wanted to get a speed of how quickly it would get from, let's say, the A wing to the F wing, we would need to take an average of everybody's speed in the hallways. So we talked about the Kelvin scale. He also talked about how to calculate absolute zero, and you might have done a lab in Chem 1. I know I usually do when I get a chance to do our gas laws. And so what we do is we measure the volume against temperature, and of course we can only measure so many, and then we draw our line, and we hope to get to as close as possible to absolute zero. In this case, it would be negative 273 degrees Celsius, or 0 K. So this Maxwell-Boltzmann distribution talks about, again, the overall motion of all the particles based on that temperature. So again, if we have this hill, most of the molecules will be moving this fast, but some of them will be moving slower, and some of them are going to be moving faster. So again, that's the average. So if we increase the temperature, we're going to have more molecules that have higher amounts of speed. Okay, so if we have, if we increase our temperature to this red line, again, we have more molecules now moving at a higher speed, because you notice this again over here, you have less molecules here moving, and here you have more molecules moving. So hopefully you got that or understand that a little bit, but again, we will talk about that later on in one of the upcoming chapters. He also, or you should have watched the video on heat exchange. So again, my notes, what does hot really mean? Well, it just means that something's at a higher temperature. It means that it has more kinetic energy. Those molecules are moving faster. So if you touch it, a lot of that energy then will be transferred to you. So we want to always remember that heat is really the energy of those molecules. So we talked about warm versus cold, and he talked about how a warm body is going to have more kinetic energy. Those molecules are going to be moving faster. And if we have a colder body, we have less kinetic energy. Those molecules will be moving slower. So then he actually put, you know, our E's in there for energy. And we said, okay, now those two pieces of, I don't remember if he used wood or metal or whatever, doesn't matter. One is at a higher temperature than the other. The thing you want to remember is that this energy now is being transferred, and it's being transferred as heat. And this is why when you do touch something that's hotter than your hand, you feel the heat. You say, oh my goodness, that's hot. Well, it is hot compared to the temperature of your hand and the temperature of the object you touched. But again, hot is really a relative term. You really want to give it a temperature value. So that's why we say heat is being transferred. The energy is being transferred. So again, energy is being transferred as heat. Just something to keep in the back of your head. He also talked about how metal transfer heats more readily than wood or brick, which should make sense. They absorb heat quicker, so that means they're going to transfer that heat more quickly. So again, if you want to, and I do recommend sometimes you go on this fetcolorado.edu and look for these simulations and play around with them. He played around with it a little bit for you, but you could also go on yourself and see what happens. So low versus high energy particles, again, he was trying to get you to understand how fast they're moving. So if you notice, you know, this molecule is moving so fast, but this molecule is moving way faster because it is at a higher temperature. So collisions between those molecules, again, think about when they're colliding. So when they're touching, this energy is being transferred. And we always want to remember that the transfer is between warm and cold. Always, 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 and forever. The collisions, you know, will be happening, but we want to remember that that energy is always going to be transferred from a warm object to a cold object. So thermal equilibrium just means that there's both substances would have the same amount of energy. So I'm going to go back here real quick. So if these two particles, these molecules, after they touch, for so long, what's going to happen here is that they're going to have the same amount of energy. They're going to move the same. They're going to have the same amount of energy. So we're going to call that thermal equilibrium. And we'll talk again a little bit more in detail about what equilibrium truly means when we get to that chapter. So specific heat capacity, again, how much heat something can hold. So if we look at these values, and you might have learned about specific heat in Chem 1 and did a lab. So if we have gold, this is just saying that it takes gold 0.126 joules of heat energy to raise its temperature 1 degree. 1 gram of it, 1 degree Celsius. Aluminum, 0.9. That means it takes a little bit more energy. And if you think about it, if you had a piece of gold outside versus a piece of aluminum, the aluminum is going to take a heck of a lot longer to warm up. Same thing with water. Look how huge that is. 4.186 joules of heat energy to take 1 gram of water 1 degree Celsius, 1 degree hotter. So ladies and gentlemen, the more the specific heat capacity just means that it takes more energy to warm it up. Okay, so think about those things. Like if you're wearing gold in the sun, or if you touch it, ooh, it gets hot right away. But aluminum foil, you can keep that in the sun for quite a long time, and it's going to take a lot of heat energy to warm that up. And think about your swimming pools. Oh my goodness, right? It takes until August until that pool water is warm. That's because it takes so much energy to raise its temperature. So now we are off to your packet, and again, I suggest you pause the video when you see my notes and then play to hear my words. So there's lots of objectives. The nature of energy, talking about kinetic and potential energy, thinking about the units, thinking about energy being transferred, and we're going to talk about how state energy changes on a particular part of the universe called the system, and everything else is the surroundings. So there's always two parts that we're going to be talking about: the system, which is actually the process or the reaction that's happening, and the surroundings is everything else. So thermodynamics is just the study of energy. Energy comes from three things: chemical bonds, and we're going to talk about making and breaking those bonds; potential energy, sometimes related to a phase change, going from a solid to a liquid or a gas to a solid; and kinetic energy, obviously the motion of those particles. So give this some thought. Read this over and see if you can answer A and B. Again, hopefully you got those answers. If not, please review that. But it's just talking about the idea of potential stored energy and kinetic energy of motion. So your units of energy, you've heard us talk about this already, as joules, and maybe you've heard of calories when you're eating things and everything has a label on them. Food has labels on them that tells you how many calories. Well, ladies and gentlemen, that's just telling you how much energy is needed for that food to basically be digested, how much your body needs to exert, how much energy your body needs in order to eat that piece of pumpkin pie, or how much calories or energy is needed to eat those 3 M&Ms. So obviously the more fat content, the more energy, the more calories is needed to do that. That's where that comes from. So the universe has two parts: the system and the surroundings. So the system is what we're concerned with. That's like usually the reaction we're dealing with, or the process we're dealing with. And the surroundings is everything else around it. So which way is the energy flowing? We have a glass of water. Is the warm water warming the ice, or is the cold ice cubes cooling the water? Hopefully you said the warm water is warming the ice, because as always, heat flows from a hot object to a cold object, always, always, and always. So transferring of this energy can be done as work or heat. So if you think of a pitcher, work is done by the pitcher on the ball, because as he's moving his arm, he's exerting that energy from his arm to the ball, and it's going fast down the plate. But if you think about heat, heat is added to the burner to make the water increase in temperature. So you can think of energy being transferred in those two ways. So here's an equation. Don't go crazy. You're not going to see it. It's not on your reference sheets, but I wanted you to be aware that this work is really energy transferred, taking the force, that push or pull exerted on an object, times its distance. So work, again, is talking about force and distance. Okay, we'll see you in class.